So you all set to go? I think we might make a start soon.
Yep. Oh, sorry, I haven't changed my affiliation. But yeah, anyway.
Oh, no worries. Okay, good. So welcome everyone to the Asia Pacific Analysis and PDE seminar, starting in after a break of a few weeks. So it's a great pleasure to introduce today's speaker, Tristan Buckmaster. He was an honours student at ANU quite a few years back, and after that did the master's at Bonn and then a PhD in Leipzig. And since then he's had positions at Courant and at Princeton. Now he's a professor at Maryland. So Tristan is going to tell us about smooth imploding solutions for 3D compressible fluids. Thanks, Tristan.
Well, thank you very much for the invitation once again. I look forward to seeing everyone in person again. So I'll be talking about work with Cal Labora, who's a brilliant PhD student at MIT, who I got to know, who spent a year at Princeton. Javier Gomez Serrano, who's at Brown, has a dual position at Brown and University of Barcelona. So let me just give some background to this talk. So this is the full non-isentropic Euler equations. So we have the conservation of momentum, the conservation of mass, the conservation of energy. So here U is the velocity, rho is the density, P is the pressure, E the energy. And the conservation of energy can also be replaced by the transport of specific entropy. I will assume an ideal gas law for the pressure. So the pressure will be of this form. For some adiabatic exponent gamma greater than 1. And the sound speed is given by this formula. And the sound speed is the speed at which disturbances propagate within the gas. So the prototypical singularity for the Euler equations is the shock wave. So the shock wave is when a disturbance, the speed of the disturbance exceeds the local speed of sound. And mathematically, one is interested in the problem of the formation of the shock and the development past the development of the shock, so the propagation of this shock. Implosion is implosions involve spherically symmetric solutions that collapse to a point in finite time. So classically, one considers imploding shock waves. So singularity, a shock is itself a singularity. So an imploding shock wave has a singularity to begin with, and then this shock implodes. Recently, Mel, Raphael, Rodiansky, and Zeftel showed that there exists smooth imploding solutions. So the solution is smooth up until the singularity. And this is a different type of singularity, and it's more interesting from a mathematical point of view than, say, a physical point of view, because these implosions are inherently very unstable, which I'll talk about that later. So just to give a brief history of shock formation results. So the shock formation is before the singularity occurs, and the shock development is after the singularity and the propagation of this shock. So Christodoulou and Christodoulou-Meyer. So the first result was in the relativistic setting, and the second result is in the non-relativistic setting. They showed for 3D isentropic irrotational Euler that shock can form. Luke and Speck extended this to the 2D case, where one allows for non-trivial vorticity. With Steve Scholar and Vicol, we considered a specific case, so the 2D isentropic, where you assume an azimuth or symmetry, so the solution only depends on the angle. And in this case, the reason why you would want to consider azimuthal symmetry rather than, so traditionally you consider radial symmetry, is that with azimuthal symmetry, you can still have non-trivial vorticity, whereas radial you can't. So what we did is we sort of thought of this as a toy problem, and we showed a singularity can occur, the shock forms, and we gave a complete description of the self-similar profile. And using this framework, we extended this to the entire, so the full problem. So in particular, the full 3D Euler, and we gave a full description of the formation of the self-similar profile of the singularity. So this, and then this was followed up by some work by Luke and Speck. And recently, this is an announced result by Scholar and Vicol. They extended these results to consider the pre-shock. So I'm not going to go into all these results in too detail in shocks because I'm going to talk about implosion. But you could imagine that so a singularity occurs when a shock forms. A singularity will generically form at a point, but you can still propagate in other areas of space-time, if you consider space-time rather than just space, rather than just time slices. In other areas of space-time, you can keep propagating the solution, and the shock will form at a later time. And then you can consider the hypersurface where the singularity forms in space-time, and this is the pre-shock. And so they showed that they constructed this pre-shock for the case of 2D Euler. And so there's a bunch of results prior that I'll just mention. Sideris, who proved the first result regarding a singularity formation in higher dimensional Euler, but it's via virial argument where you don't know the form of the singularity. And Alanak, who considered the case of nonlinear wave equations. Unfortunately, this result gives a quite complete picture, but it doesn't cover Euler. So shock development is after the singularity is formed. So there was a brilliant PhD thesis by Lebeau, who considered 1D, 2D, 2x2 P systems, and they showed the existence of discontinuous shocks. And this result was extended by typing Liu, Chendong, Kong, the generalized result. Also, typing Liu, from typing Liu's result, you get uniqueness, and extensions are by Chendong and Kong. Yin extended this framework to prove spherical symmetric or spherically symmetric shocks occur. So there exists a weak solution past the formation, although one doesn't have uniqueness, and one doesn't have a description of weak discontinuities, which I won't actually describe in this lecture, but this is another phenomena that happens after a singularity. So there's a shock forms and the shock propagates, but also you have these weak discontinuities that also form. Christodoulou and Lisbeth also considered the spherically symmetric case, and they have a more detailed description, although it's not actually the solution to the actual Euler equation. They consider a reduced equation, and so you get to a sort of, they get a solution to this reduced equation. And they extended this framework to the multi-dimensional setting, so without any symmetry. And they also constructed, so Christodoulou constructed, developed shocks, but in this restricted problem, so you don't actually get a solution to Euler. With Drivas, Scholar, and Vicol, we showed that in the case of azimuthal symmetry, and remember azimuthal symmetry maintains a lot of the interesting properties like non-trivial vorticity, we solved the full problem. So we did the full development where we have uniqueness, and we also have the first full description of these weak discontinuities, which I won't talk about in this lecture. This is an old conjecture that goes back to Landau and Lifshitz. So now we'll talk about implosion. So these implosion results go back to Goodley in 42. He considered self-similar imploding shock waves. Of course, it's not the nicest history of what these results. I mean, you can kind of guess what these results, why people were interested in this at the time, in 1942. So these, but in any case, what happens is, to simplify the problem, they considered a problem where singularity has already formed. In particular, they have self-similar imploding shock waves. So this implies that a singularity has formed. So in particular, in a shock wave, you have a discontinuity in the velocity and the density. So Merle, Raphael, Rondianzi, and Sefto showed that there exist smooth imploding self-similar solutions for almost every adiabatic exponent gamma greater than 1. And I'll make this clearer why this condition for almost everywhere comes into play. Biasi, in a numerical paper, provided a very detailed description of these imploding solutions of Merle et al. Related work. So, so for a form of compressible Navier-Stokes, the solutions used in this paper were used to construct solutions which form a singularity for the compressible Navier-Stokes. And they also showed that in dimensions 5 and higher, that they could use these solutions to find singularities for defocusing NLS. And this was an open problem of whether defocusing NLS could form a singularity at all. And this is via a well-known transformation between Euler and NLS. There's another beautiful result by Gao, Hadzik, Young, and Schrecker, where they consider Euler-Poisson equation. This is slightly different, but many similar techniques that they used in this paper will also appear in the work that I'll describe. Okay, so let me now bring the setup for implosion. I will restrict to the case of isentropic spherical. So in implosion, we consider spherically symmetric Euler. So you end up with these two equations for the velocity and the density. So in isentropic, the entropy is constant. So you drop that equation. So now with this, now I'm going to take a self-similar ansatz to reduce the equation. So I'm going to take U to be in this form. And so sigma is just going to be a rescaling by a constant of the sound speed, and it will be of this form. Now let me just there's first of all there's a typo here. This should be a capital R, and this should be a capital R. Somewhat confusingly is I use the lowercase r as a self-similar parameter that describes the how the solution self-similarly scales. Capital R is the radial variable here. Okay, and so this should be capital R, and this should be capital I here. So one makes this ansatz, and so this is your new this is your new spatial variable. This here. So let's call this psi. And if one writes the equation in this new coordinates, self-similar coordinates, you end up with an autonomous ODE. So you completely remove time from the equation, and if you can construct smooth solutions to this ODE for all R, then you end up constructing a solution which implodes. Okay, and this is just embedded in the self-similar coordinates. And what one thing that you'll see is one thing that's important in this for this implosion is that both the velocity and the density will go to infinity at the time of the singularity. So there's a very different type of singularity that you would have for a shock. So in a shock, the velocity and density stay bounded. So since we have an autonomous ODE, we can draw a phase portrait. And what these lines are, so these the black and the red lines, sorry, the red line is the denominator, so this denominator here, and the red and the green lines are the two numerators. Now, if you want to construct a smooth solution defined for globally, so for all capital R, you need to find a curve that follows this phase portrait, which connects P infinity, where the radius is infinity, to P0, where the radius is 0. Now, the problem with doing that is that you cannot cross this black line, sorry, this red line, because this is when the denominator vanishes and then you get something infinite. So you can't cross this red line, and so but this red line divides P0 and P infinity. The way you can get around this is you can actually cross this red line, but you can only cross this red line at this triple point, where both the numerators also vanish. Now, the Goodley solutions correspond to solutions which cross in terms of this eigenvector, which I'll describe how these eigenvectors come into play later. Whereas the solutions of Mel et al. Cross with this eigenvector. Now, the solutions of Goodley, you'd cross like this, and then you'd immediately hit this red line again, so it wouldn't be a global solution. The way to resolve this is that you introduce a discontinuity which allows you to jump from one place in the diagram to another. So you go up through here, and then you have a discontinuity which jumps down here, and then you can continue on to P0. So this is it's not a smooth solution, and this is why you're required to have a shock. Now, the Mel et al. Solutions, they cross with this nu minus, and for certain special choices of the parameter lowercase r, self-similar parameter, they can actually construct solutions which connect P0 and P infinity. So this is the result. So for almost every gamma, there exists a countably infinite sequence of self-similar solutions to the isentropic order. The velocity and density blow up at the origin. Now, the condition on gamma relates to some non-vanishing of an analytic function. And so this is why you get this almost everywhere, almost every gamma greater than 1. The condition isn't proven for any specific gamma, but they check it numerically. The case for gamma equals 513 is, which is important because it corresponds to monatomic gases, is ruled out for other reasons. So this is the compressible Navier-Stokes that they consider. They consider the case of isentropic 3D compressible Navier-Stokes, where one has constant viscosity. So in particular, viscosity doesn't depend on any of the variables. In a more physical system, you would introduce temperature and also have a viscosity depending on temperature. But this is another model. So one has these relations on the two viscosities, and what they prove is that for almost every gamma within this range from 1 to 2 plus the square root of 3 on the square root of 3, there exist solutions which smooth initial data, which leads to a singularity of the same form as the Euler singularity. One caveat is that they require decaying density. You don't really want to have this as a requirement because you'd like to say that the singularity doesn't have anything to do with the far field. But anyway, it's mildly decaying. Previous results by Sim showed blow-up initial data with compact density, and Rosanova showed for blow-up with rapidly decaying density. But these are very different types of results in the sense that they don't tell you anything about the singularity. They just tell you certain settings for the singularity occurs, whereas this tells you the actual profile, the self-similar profile of the singularity. So open problems from the results of Mel et al. Do imploding solutions exist for all gamma greater than 1? And can one construct imploding solutions of the Navier-Stokes equation? And by this, I mean this compressible Navier-Stokes equation here, with initial density constant at infinity. So this last condition rules out the far field having any role in the singularity. And this is our main result. There exists smooth self-similar imploding solutions for all gamma greater than 1. And for the particular case of gamma equals 7/5, which is diatomic gases, so the air we breathe, there exists a countably infinite sequence of imploding solutions. The reason why, it seems like something nice to have, but it's not quite clear why I would want this countably infinite sequence of imploding solutions. The reason is that as you go further down the sequence, the self-similar parameter R increases, and it allows you to deal with other terms. So, for example, in the case of the Navier-Stokes equation, the larger R is, the more you can deal. I'll make this more precise on the later slide. The easier it is to deal with the viscosity and to count that as an error. So this is more a mathematically interesting thing, and this is also, so if you want to sort of think of this in a broader sense, if one was actually considering the incompressible Navier-Stokes equation and one wants to prove the Millennium Prize. So one possible approach to proving the Millennium Prize would be trying to construct a self-similar solution to the incompressible Euler equations, which such that profile is the profile of the singularity that forms the Navier-Stokes equation. And one would imagine that if you could do such a thing, that it's quite likely that the profile that you construct is highly unstable. And so as you move down this sequence of self-similar solutions, these self-similar profiles become more and more unstable. But the more unstable they become, the more you can deal with viscosity. And this is something that's actually, so this is used in this case for compressible Navier-Stokes, but it's also known simpler settings such as the Burger's equation and dissipative Burger's fractionally dissipative Burger's equation. The more unstable the self-similar profile, the more you can deal with dissipation. I don't want to say that this is at all as easy as difficult as the actual Nobel Prize problem, because inherently the self-similar profiles that we construct here are one-dimensional because we have this radial symmetry, whereas at the best case scenario is that for Euler equations, at least the self-similar profiles have to be 2D. So that's if you consider say axisymmetry. Anyway, so that was a minor digression. So we also proved simpler proofs for linear stability and non-linear stability. And we showed that for this case of diatomic gas, that we have a self-similar imploding solution. And this is the first example of initial data where you have density constant at infinity, which leads to blow up for this particular Navier-Stokes equation. Okay, so the first thing we do, and this is motivated by my previous work with Scholar and Vicol on shock waves. It's useful to rewrite the equation in terms of the Riemann invariance. So if you take these self-similar ansatz, which is just like the self-similar ansatz we had before, but in terms of the Riemann invariance, you end up with these two equations here. The main difference when you write things in terms of the Riemann invariance is that it somewhat diagonalize the equations and you end up with just nonlinear transport equations. So this is, well, okay, so in the original variables, it becomes nonlinear transport equations. But in these, with the self-similar ansatz, it's particularly simple. There's only one derivative here. You also end up with these ODEs. We have, and here NW is the numerator and Z is the numerator for Z, and the denominators are denoted by DW and DZ respectively. Now the picture looks slightly different. So the reason why I only draw this triangle is because this is where the density is less than 0. So when you can consider cases when the density is positive, and I've compactified everything to make this into a triangle. I also compactified in the previous, this is also compactified, I should say. So in this case, you want to connect P0 and P infinity. Now the red line is where the denominator Z is 0, and the magenta line is where dW is 0. And in this case, when you're crossing, you only have to cross the red line. So in particular, the singular part of the equation is only in one variable. So this is one good reason to use these Riemann invariants. And in fact, you have a very geometric picture of what these implosions look like in these Riemann invariants. So now let me get this correct. So so if you think of so these so you can think of these as sort of sound waves, and the Z wave. So one thing is that so how do I describe this? So there's this particular point, PS is where you have to cross. This is a singular point, but there's one thing is that information outside of, so you could also draw this picture on like from radius equals 0 and self-similar coordinates to radius equal infinity, and then you can place, say, PS at 1. So you can fix it to be 1. And then from 1 to infinity, nothing of the solution here actually influences anything from 0 to 1. Okay, so once you cross PS, you can't send any information back to this region. And in physical coordinates, this region, of course, is shrinking, but in self-similar coordinates, it stays the same. So you can think of, if you think of them in terms of z waves and w waves, the z waves from this point, say from 1 to 0, they will be traveling in the direction towards the origin. Of course, it's in radial coordinates, so they'll actually cross the origin because it just is in radial coordinates, so it goes on the other side. But you can think of it being once the z wave gets to the origin, it gets reflected back as a w wave, and it goes off and goes past this point PS. So information can be sent out of this region, but it can't be sent in. Anyway, this is a sort of geometric picture of what happens with these imploding solutions. So a lot of the analysis, a large part of the paper is dedicated to analysis around this the singular point PS. It's useful to, again, rewrite, make a change of coordinates to desingularize the ODE. So here in these new coordinates in terms of psi, you desingularize the ODE, and PS becomes a stable stationary point. Now, just to make make life simpler, let's consider the simplest so two-dimensional ODE you can imagine. So x dot equals lambda plus, y dot equals lambda minus y, where lambda minus is less than lambda plus is less than 0. So if you take k to be the quotient between the two eigenvalues, and if k is not an integer, then x equals 0 and y equals 0 are the sole smooth solutions. So again, this is why we end up having these two eigenvectors here. It relates to this kind of analysis in this simple setting. One does have, however, a whole range of non-smooth solutions, CK solutions, which are of the form y equals some constant times x to the k. So these are not going to be smooth because we assume that this k is not an integer. So this is the picture. So you have a smooth solution, y equals 0 here, so x equals 0 here, and y equals 0 here, and then these are the non-smooth solutions. And the same thing happens in our setting. It's just a more complicated ODE, but you have the same type of solutions that appear. So if we return to this equation, to our ODE written in this new coordinates, then it's important to have to consider this k, which is the ratio between the two eigenvalues. And the corresponding eigenvectors are those two directions that I showed you in those phase portraits. And we'll consider the solutions which are tangent to nu minus, whereas Goodley considered the case of smooth solutions which are tangent to nu plus. So again, this is a picture. We'll take the solutions corresponding to nu minus because the ones with nu plus will hit this magenta line, which is when the denominator in the W equation vanishes. So if one does so one way to do this analysis around this singular point is to do a Taylor expansion of the smooth solution at this point. You end up with these two equations. And the important thing to, if you remember, I said that only the denominator of the z equation vanishes. So this is the The Z equation is the most important. The W is not so important. It's not so singular. And the reason, so when you're solving the equation for Z, you can solve this. You can solve this for the Taylor series in an iterative fashion. One thing you see in this equation is this n minus k. So n is the Taylor coefficient, and k is again this quotient of the two eigenvalues. Now, when this vanishes, then the Taylor coefficient doesn't exist, and so this was this condition before, related to this condition before in terms of k. So this is another way to see it. And one thing to keep in mind is that when k goes below an integer and then crosses past an integer, so say the integer is say 2, and it crosses from 1.9 to 2.1, there's something singular going on. So the coefficient will get very large because it's very close to an integer, and this, when you divide by n minus k, you get something very large, but also change sign, and this will form some sort of wiggling in the solution, which we'll exploit in order to construct these smooth solutions. So we'll make a restriction on this self-similar parameter R, and this is just a restriction such that the picture that I showed you in terms of the phase portrait stays the same. If you go beyond this range, then the phase portrait looks very different, and you just cannot construct these solutions. Now, k in the range from 1 to r star, k is an increasing function going to infinity, and this is what will allow us to create a infinite family of self-similar solutions. Let us define, sorry, figuring out a bit of a cold or something. Let us define Rj to be the values of the self-similar parameter R such that k is the integer j. So we want to connect again this p0 to p infinity, and how we're going to do this is let's just take n to be odd, and we'll consider the self-similar parameter between Rn and Rn plus 1. And what we show is that to the left of PS, the solution will converge to P infinity. So in this range, the smooth solution will always hit P infinity, which is a good thing. On the other side, on the right of PS, if R is very close to P, very close to Rn, then the solution will intersect the line dW, which goes below. And if it's very close to dn plus 1, it will go above and hit dz. Of course, none of these two scenarios are good in the sense that they don't converge on P0, but since one goes down and one goes up, by continuity argument you get, or shooting argument, you get there exists one R in this range from Rn to Rn plus 1, such that the solution actually reaches P0. So for gamma greater than 1, this is shown we fix n equals 3. And for gamma equals 7/5, this is shown for all odd n sufficiently large. And so this is done via barrier arguments. You want to find curves in the phase portrait which bound the solution and force it to either go to P infinity, or go to P, or on the other side go to NW, or to go to NZ. in the particular case of gamma equals 7/5, we exploit the fact that if gamma is less than 5/3 and n is fixed, then these coefficients converge as r goes to r star, to something non-trivial. Then we can see this. We need to see this wiggle that we saw before, and this wiggle can be determined so long as we know we have the sign and some lower bound on the higher order coefficients. And how this is done is via computer-assisted proof, where we compute the first 10,000 coefficients, and we compute this with the effective bounds. So we know the solution is, the coefficient is this number plus or minus something. And this is proven rigorously via interval arithmetic. And then if you can do the first 10,000 coefficients, then you can do a simple inductive argument to keep continuing on. So one thing to keep in mind is that the solutions we actually construct in this gamma equals 7/5 case are incredibly unstable. So you'd never see them on a numerical simulation. They're unbelievably unstable. The proof works for general gamma less than 5/3. However, the computation degenerates at gamma equals 5/3. I will go through these last couple of slides quickly, as I guess I've run out of time. Maybe how I would do I have a couple of minutes or?
Yeah, sure. A few more minutes is fine.
Yeah. Okay.
We started a little bit late. So.
Okay. So I described somewhat how to create these Euler profiles. Now I'll just give a very quick description of how you go about using these Euler profiles to prove singularity formation for this compressible Navier-Stokes equation. The basic strategy is you linearize the Euler equations around the self-similar profiles. You show that the linear operator has finitely many unstable modes, may have a lot of unstable modes, but you show that there's finite number, and then you apply a topological argument to show there exists some initial data which leads to asymptotically to this Euler profile. And the main thing to keep in mind is that when you write, so if you write the compressible Navier-Stokes equation in self-similar coordinates, but you keep an extra variable which corresponds to self-similar time, then you have these extra terms which correspond to dissipation. They look horrible, but the main thing to keep in mind is it has this term here which depends on self-similar time. And the only thing that you really need to care about is that this exponent is negative. So in particular, dissipation can be treated as an error. And so you want that the Euler part of the equation dominates. For this to be treated as an error, you want R to be as large as possible. And you need that R is greater than 2 gamma on gamma plus 1. And this is where you get this restriction of the adiabatic exponents. And this is also why you need these very unstable solutions, because the more unstable they get, the larger R can be. And yeah, I won't go into the. I'll just say one thing is that the main part of the linearization argument is that you want to show that the linear operator is a maximally the modular compact operator is a maximally dissipative operator. That's the main trick, and then you can use sort of abstract functional analysis to show this. So yeah, I'll leave it there, and then I can answer questions if people want more details about it. Great.
Thank you very much, Tristan. A very interesting talk. So if anyone would like to ask a question, you can raise your hand, and I think Daniel can unmute you and you can ask it. So please feel free to do that. Also, Daniel's just posted in the chat, everyone is most welcome to join us for the coffee break, just to get together for a more informal chat after this talk. And you should all have received an email with the details with a Zoom login for that. Yeah, so Tristan, just a quick question. Do you have a sort of dynamical understanding of the instability here? That if you, somehow you're threading this line between, in the ODE, you can clearly see how it's unstable, but does that turn into, for example, formation of a spherical shock before the singularity or some other behavior like that? Can you understand things that way?
That's what I imagine happens. So in basically any, that if you modify any of this initial data by a small perturbation, a shock will form first. And it would be interesting to know if that then implodes. But that's basically what would happen. A shock would form first. The hard, one of the hard things to deal with, the shock development part is actually very difficult. So the following on this, we only had this recent result regarding the full development problem very recently, and that was the first result in actually any setting in 1D or anything like that where you have the full equation. I think one thing I think that is, there's a lot of results where you start from a shock and then you continue it on. There's a lot of results where you start from a singularity and you continue it on, but there's not our result was the first one where you start from where the singularity forms, and you then propagate the shock. And the big difficulty here, or one of the big difficulties here, is that so I'm sort of digressing, but in answering your question, that it would be a very interesting problem in having a shock form and then imploding. But I'm just saying that it'd be actually quite difficult to study that problem, although it'd be very interesting.
I imagine so, yeah. And
the difficulty is in what these weak discontinuities, because if a singularity forms, the shock is not the only discontinuity. Okay, it is actually the only discontinuity, but there's these other hypersurfaces which are weak discontinuities, which just means that higher derivatives are continuous. And if I actually show you, I can show you a video of this where you can see these weak discontinuities, and you'll probably just think that the numerical fluff, like they don't look like anything because they're not the higher derivatives. You wouldn't actually notice.
I saw Vlad Vikol's ICM talk where he showed some of this, I think.
Okay.
That's all on YouTube for anyone who wants to have a look.
Yeah. So that's but yeah, it would be a very interesting problem to actually study the problem where shock forms and then an implosion occurs. But I imagine it's quite a difficult problem. And that would be the physically relevant problem, whereas this is not physically relevant.
Yeah. Sure.
Never happened.
So I noticed you had a preprint which seemed related to this, where you did numerical approach to this using some kind of neural network thing. Was that actually related to this problem, or was that something different?
Well, that's incompressible. So
that's incompressible. Yeah, I see.
That's related to incompressible Euler.
Okay.
And so that's what I was describing. So that's why I was describing the incompressible problem is so much more difficult, because you have this divergence-free condition. So you cannot have these 1D. You can't have these 1D solutions. It has to be 2D, and you can't use these ODE arguments that we. These beautiful. You can use the ODE argument because it's a local. Because you have finite speed of propagation, and You don't have any of that for the incompressible case. So
the self-similarity would correspond to some stationary PDE problem rather.
Yeah, it was but it would be very hard to do it by hand to find them.
Yeah.
So in the recent preprint, we use neural networks to find them. And so this is becoming actually a very big project. It's all numerical at the moment, but the one thing is that we know that they're the right solutions. So they are. So in that case, it's Euler outside a cylindrical boundary. But we hope that we can also use this to prove existence of solutions without any boundary at all. And we can find a whole lot of the solutions that you just we can find unstable. One nice things about these, really digressing from the talk, but one of these nice things about these neural networks is that you can find these unstable solutions. So like in this paper, we showed that you can use these unstable solutions to construct solutions to compressible Navier-Stokes. How are you meant to find these unstable solutions to incompressible Euler? I mean, you can't simulate them because they're unstable. You'll never find them. And with this neural network approach, where you just solve the PDE directly and you look for the self-similar parameters, you can find these unstable solutions.
Yeah. Very interesting. Okay, so I don't see any other questions at this stage. So I think we might leave it there. So I think, Tristan, you should also have received an email with the details about the coffee break. So that's just an opportunity to chat a bit more informally. But for now, thanks again for a wonderful talk, and talk to you soon.
Thank you, Ben. Okay.